don't seem to be allowed to full screen because it thinks my resolution is something different from what it actually is. I'll figure that out another day. All right. So any problems with the homework? Pretty straightforward. All right. So as promised, let's talk about state machines. And I'm not going to look at building state machines, but I want to look at making state diagrams and thinking about what state machines can do for us. So here's a general, we're going to stick with finite state machines. There are machines that have infinite numbers of states, but you need an infinite state memory for that. So here's a general view of what a state machine looks like. It's a set of 4 tuples: present state, input, next state, and output. And these are the sets of columns from those dreaded wide state tables that we make in 250, right? Current state, what's coming in, and for each combination of those, you define what the next state is and what the outputs, if any, are. And we can get mathematical with this if we like. So here's a state machine M, and it's a sextuplet of S, I, O, F, G, and S0. So this is the set of states, this is the set of inputs and outputs. F takes an ordered pair, which is a state and an input, and maps you to a new state. And G takes an ordered pair, which is a state and an input, and maps you to an output. And S0 is the initial state. And we don't need to think of it like this, but we can, right? So we can be very formal about it. But the basic behavior is you have a collection of states, right? And the state is, and if you've done 250, you probably have an idea what a state is already. It's kind of an abstract notion. It's just sort of what position the machine is in at this point in time. And depending on its state and the inputs, the machine is going to do something. And what it can do is it can generate outputs and it can go into a new state. And it turns out everything we do with computers today we can break down into just a big glorified state machine. Okay, your laptop, your cell phone, those are state machines. But we don't program them in terms of these state transitions. We program them in high-level languages or maybe assembly language. But it's certainly a state machine. So we have some state machines that have no outputs. They just move from one state to another. They take inputs and they move from one state to another. But certain states have certain significance. They're what we call recognized states. And we may have a machine that takes input and just moves from state to state and simply answers the question, am I in a recognized state? And we can use these for things like language recognition. If you want to know if a C program is valid, you could make a state machine. You should start feeding in the source code from your C program. And after you feed in the last curly bracket, if your machine is in a recognized state, it means that it's a correct C program. Or it means that the program eventually does something, or whatever your analysis is for. So those things are called finite state automata. And it's just a state machine without outputs. And we'll look at those for language recognition in a little bit. So if you had 250 with me, you've probably seen this example. If you had it recently with me. So this is branch prediction. So really briefly, think back to 270 if you've done 270. Microprocessor trying to run really fast. To execute an instruction, you need to pull the instruction from memory, figure out what it's asking you to do, and then do it, right? So we have basically two steps: fetch and decode and execute. Fetch and decode, execute, right? It turns out in general, those two steps are independent of each other, so we build what's called a pipeline. And while we're fetching and decoding one instruction, we're executing the previous instruction. When we execute that second instruction, we're fetching and decoding the instruction after it. We're doing two things at once. And modern pipelines can be 10, 15 elements deep. So at any given time, we're actually working on, say, 15 different instructions simultaneously. And the effect is the same as an assembly line. We complete one instruction 15 times faster than if we just did one instruction from start to finish and then began the second instruction from start to finish. So if you haven't done 270 or you don't remember that, don't worry too much about it. It's a build-up to the punchline of this story, which is when you have to do a branch, when you do a go-to, when you're not executing the next instruction, that pipeline breaks, right? Because pipelining works because while we're doing this instruction, we're finishing up the instruction before, we're finishing up the ones before that, and we're getting ready to do the ones that come after. If it turns out we're not going to do those instructions that come after, all of that work that we did ahead of time is wasted. And we do what's called flushing the pipeline. We go off to where we're supposed to be executing instructions, and for the next 10, 15 cycles, all we're doing is filling up the pipeline. So it's called a pipeline stall, and it's the performance killer on modern processors. And the thing that stalls your pipeline most often is a branch. You're executing instructions sequentially, but all of a sudden, instead of doing this instruction, you got to go over here and do those instructions. Okay? And that kills your performance. Now, if you knew ahead of time, like up here, that when you got here, instead of doing the next instruction, you were going to go over here, no problem. As you're pre-fetching and pre-executing your instructions, when you get here, next instruction you fetch, just grab it from over here, right? And the branch is not a problem in that case. So if you see something like a go-to instruction, you don't have a pipeline problem. But if you have a conditional branch, which says if my zero flag is set, then go over here, well, you don't know if you're going to go over there until you get down here and you know, is the zero flag set, right? You got to be able to predict the future and say 7 instructions from now, when I get down here, am I going to take that branch or am I going to do the next instruction? And if you can guess correctly, you can keep your pipeline full, you get that great throughput. Everybody wants to buy your machine. If you don't guess correctly or you don't guess at all and you just get a pipeline stall, nobody wants to buy your machine. So branch prediction is being able to tell ahead of time, are we going to take a branch or not, without actually knowing what the state of the machine is going to be. And it turns out there's a pretty successful way to do branch prediction. It's called 2-bit branch prediction. Say it 3 times fast. And so here's what a 2-bit branch predictor looks like. It's a state machine. And we have 4 states. And this machine predicts, are we going to take the branch? When we get to this conditional branch, are we going to actually branch somewhere as opposed to just falling through the next instruction? So we have 4 states. This is called the strongly taken state. We really believe we're going to take the branch. This is weakly taken. We think we're going to take the branch, but we're not really convinced. We wouldn't bet $1 million on it. But I think we're probably going to take the branch. This is the weakly not taken, not convinced, but I think we're not going to branch. And this is the strongly not taken. Really don't think we're going to. And we have one input to the system. And the input is, do we branch? So here's our little diagram. There's an input, there's no output. So this input is a 1 if we ended up taking the branch, a 0 if we did not. So it's our branch input. So suppose we're in a state where we really believe you're going to take this branch. And we eventually get down to that instruction and we check the condition, and it turns out that based on the condition, we did take the branch, right? So we guessed correctly. So our input is a 1. We're going to stay in this state. So the next time we come down here, we're going to say, yeah, I still think we're going to take the branch because we just did, right? But if we believe you're going to take the branch and we get down here and we test the condition and it says, we're not going to branch, right, that's a 0. Well, we're not going to totally change our prediction, but we're going to say, yeah, I think you're going to branch next time, but I'm not totally convinced. So we'll go to the weakly taken condition, right? And this means we got a pipeline stall. But we believe the next time you get here, you're going to branch. And so the next time that you're coming down this instruction stream, when you get to this instruction, next one, you're going to fetch from over there, right? Okay, if you're in a weakly taken state and it turns out that you do branch, we say, aha, I knew it. That time you didn't branch was just a fluke. So now we again strongly believe that you're going to take the branch. But if we only kind of believed you were going to branch and the next time you get there, you end up not branching, now we're going to change our story. We're going to say, okay, I don't think you're going to branch the next time. Basically, 2 times in a row you did not take the branch. Now we're going to say, okay, I don't think you're going to do it the next time. And if it turns out the next time, in fact, you do not take the branch, now we're going to say, oh, okay, you're never branching. Right? 3 times in a row you didn't take that jump. I don't think you're going to take it next time either. So we go into this strongly not taken state. But if we kind of believed you're not going to branch and you ended up branching, then we kind of come back up here and we say, okay, well, I kind of think you're going to branch next time. So we go back to weakly taken. If you're in strongly not taken and you don't branch, we'll stay in strongly not taken. And if you do branch, we'll go to weakly taken. Well, that's a state machine. And if you implement this and you feed it an input which says, did I branch or not branch, right, it will move around from state to state. And basically any time that it's in one of these states, we say that it's going to branch. And any time that it's in one of these states, we predict it's going to not branch. So these are the predictions that feed our pipeline logic to say, should we fetch the next instruction or should we fetch the instruction from the branch spot? And this does a really good job of predicting branches because of the way we write code. Because the most common, probably the most common case for branching through a location again and again and again is at the bottom of a loop. So you're doing some kind of loop, you execute some stuff, and then if some condition is true, you're going to go back up to the top. Think of a for loop, okay, or a loop that's reading until you hit end of file. You write loops because you expect things to happen more than once or twice. And so typically, when you get to a conditional branch, there's a good chance you're going to go back and you're going to repeat this a bunch of times. And if you're doing a loop for I equals 1 to 1,000 times you're going to branch back up to the top, and then one time you're not going to, you're going to fall through, right? So this is certainly going to handle that case. But if we only had a 2-state machine, a 1-bit branch predictor, as soon as we didn't take that branch, we'd say, okay, I don't think you're going to branch next time. Well, the next time you come into that loop and you're ready to loop 1,000 times, your prediction is going to be wrong again because you're going to be saying, I don't think you're going to branch, and the first time through you do branch. So this avoids that. It basically handles nested loops. And nested loops are just very, very common in typical programs. So this is built into most processors that have any kind of pipeline inside. It's a way to do branch prediction. And it does a pretty good job. So we can also use this for weather prediction, right? So this could be strongly believe it's going to be sunny, weakly believe it's going to be sunny, weakly believe it's going to be cloudy, and strongly believe it's going to be cloudy. And our input could be 1 equals sunny and 0 equals cloudy. This is for places that don't change between sunny and cloudy 80 times a day, like around here. But what does this say, right? If it's sunny today, we think it's going to be sunny tomorrow. And if it's sunny tomorrow, we think it's going to be sunny the next day. If we get 1 day of cloudiness, we're still going to predict that it's going to be sunny tomorrow, right? Because this is like a sunny trend. And if it's sunny, we go back to here. If it's cloudy 2 days in a row, then we say, okay, tomorrow's going to be cloudy. And if it's cloudy a third day, then we say, okay, we really believe it's going to be cloudy for the next few days. And it has to be sunny for 2 days before we start believing it's going to be sunny.
Are there more than 2 bits predictions?
So, oh, yeah, you can. But I don't know if they buy you that much more in implementations like this. But yeah, so the 2 bits refers to the number of bits we need to store the states. We got 4 states, 2 bits. You could make an 8-state branch predictor, right? And you could have, strongly taken, weakly taken, very weakly taken, and then something else.
For the most part, this doesn't make much sense.
For branch prediction, it's usually 2 bits. And I think it's largely motivated by that idea of nested loops. But for other situations, sure, it could make more sense to have more states, more bits. So how many people here spend time on the East Coast? So East Coast weather is kind of different from out here, right? It's like it's sunny for a week and then it'll like rain for a few days. Or it might rain for 2 weeks straight and then it'll be sunny for like 3 weeks. It doesn't really go back and forth. What?
Not in Florida.
Not in Florida, yeah.
Same day.
Right. So like inland, like I grew up in New York State and I was a few hundred miles inland. And weather basically comes across the country on the jet stream. And you can pin down really, really accurately like what the weather is going to do because it like builds all the way across the land mass. So it tends to go in waves, right? So something like this might make sense for that. Florida or out here or Hawaii where it like rains every afternoon at 4, not so much. All right, so that's kind of a real world state machine, right? It's inside processors. You can build other things with it. And the state table for this would be, if you're in the strongly taken state and your input is a 0, then go to weakly taken. If you're in strongly taken and your input is 1, go to strongly taken. If you're in weakly taken and your input is 1, go to strongly taken, and so on. So present state, input, next state. And there's no outputs here, but we could have an output for what our actual prediction is, branch or don't branch, and so on. Okay, well, we can use, let me do one more, since you're going to have nightmares anyway. So let's do a traffic light. Let's do a 4-way intersection, okay, because we're sick of 3-way intersections. So north, south, west, east. We're not going to build any circuits for this, okay? We're just going to make a state diagram. Can I get something better if I go on photo? That doesn't matter. And there's no priorities here, okay? Whichever car comes up is going to get to go. So let me define a set of states for you. West-east green means that west-east has just turned green. West-east green 2. Let me call it west-east green 20. Means that west-east has been green for at least 20 seconds. Okay. West-east yellow means west-east is yellow. And then north-south green, north-south 20, north-south yellow. Same meanings as for west-east. So here's what we want our light to do. We're going to start off with, north-south being green. And it should stay green for at least 20 seconds. And if a car shows up on west-east after at least 20 seconds of green on north-south, north-south should turn yellow for 5 seconds, and then it should turn red, and then west-east should get a green light. And that'll stay green for at least 20 seconds until something shows up on north-south, and then same thing happens. West-east goes yellow for 5 seconds, turns red, north-south goes green. So state diagram for this is actually really simple if we're not bound by engineering 250 rules. So here's north-south green. And we're going to have a transition which I'm going to label as 20 seconds have passed. So when we go into this state, we're going to start some timer, and after 20 seconds have passed, that timer is going to output a 1, right? And that's what this transition is triggered by. So basically, after the 20-second input has passed, we're going to go to north-south green 20. And we're going to stay in this state until we have a west-east car. So west-east car, 1 means there's a car, 0 is not. North-south car is the same thing. So when a west-east car shows up, we're going to go into this state, which is north-south yellow. And we're going to start another timer and wait for 5 seconds, and after 5 seconds, we're going to go into this new state, which is west-east green. And after 20 seconds, we'll go into west-east green 20. And then when we have a north-south car show up, we'll go into west-east yellow. And then after 5 seconds, we'll go to north-south green. And we can set the colors of the lights very easily. West-east green means the west and east are green, north-south is red. West-east green 20, exactly the same thing. West-east yellow means west-east is yellow, north-south is red. North-south green means north-south is green, west-east is red. Same thing here for north-south 20. And north-south yellow means north-south is yellow, west-east is red. And there's your state diagram, and it's a big loop. Right? It just simply moves from one state to the next based on these different input conditions. Now building that, is a pain, right? Because you have to have timers and sensors and all that kind of stuff. But from the level of state transition logic, it's a fairly straightforward mapping, right? And this is really what traffic lights do. They just move through this cycle of different conditions. So it's a pretty powerful way to envision, at least architecturally, lots of different machines, right? And you can make a state machine for a CPU, right? The whole fetch, decode, execute, and what happens when you say increment, and what happens when you say branch if not 0, is just a big, horrendous-looking state diagram. That's not usually how we design those things, but we can think about them like that. So we can build lots of useful machines with these, but we can also do language processing. So let me give you a state machine. And I'm going to have you go to the board, so if you want to go find a spot on a board, go ahead and do that while I put this up here. And I'm going to ask you to explore this and figure out what it's doing. So this is an analysis question. So our transitions are labeled with an input bit and an output bit. And we have two states, and I'm putting a star here. And the star means this is our initial state. And your input to this system is just some patterns of 1s and 0s. And the question is, what does this do to that pattern of 1s and 0s that you feed in? So go ahead and find a spot on the board, play around with this, and see if you can figure out what it's doing to an input string.
I was paying attention. Like a one shot, one. This for inline. Alright, so if you're in state one, then where third row. So you have one and then send your output with and
There was not what I expected. See if I can type upside down.
This is just like oh, it does matter. This is our input. Is it just looking at it's not free?
and then you want to
The bits right there. It's
No, you need our.
Zero one.
So would it automatically split?
You don't have to use that bit
Wouldn't
string,
it
that's just an
until it
example.
has valid input? Yeah,
So
so
we're
where we
here,
need a 0 1 0 or 1 by 1. So the first input would be this.
It would go from S1 to 0.
No, I don't think it's gonna go by 3. It's just gonna like read 1 by 1 until it gets the pattern. And then
So
the
it
pattern.
starts here, it that one's here, this one's here.
Yeah, and then it's gonna go here.
I don't remember how to do it.
1 1 0 0 1 1 0 1 here.
Present state 1, 0,
Does it say if the states?
yeah.
Back to the zero.
Alpha is 0.
And then it's like, it's gonna go back to the previous.
Same, present state 1, input 1, you'll
It's only that.
and next state 0.
One out of a get would be this.
What is this doing?
It's doing something to this data right here.
Is that a 1 or a 0?
So every other number
Yeah,
switches.
perfect.
No matter what.
Does that make sense from the diagram?
Yeah.
See where I got you?
Yeah, because if you start here and no matter what, the numbers are going to stay the same, but if you're here, they're always going to switch.
Right, okay, cool.
Oh wait, those are slashes.
So,
Apparently those are all slashes. I didn't even know.
No matter what, we just said.
That makes a little bit.
Oh, yeah.
I literally wrote that as my answer. Output.
where, what is this?
Are you going to hit,
I think it's just like a flash.
The one on top is the input and the one on the bottom is the output.
It'll just switch all of them. It's like, so if you have a 1, it'll go here, and then this, on a 1, it goes to 0. This is the output.
All those are all slashes too. Oh, yeah, they are.
Yeah. So like, if you go in with a 1, then your output's gonna go to 0, and then your output's gonna go 1, 0, 1, out, 0, 1. Similarly, input is a 1, yeah, and your output is currently 1. And then you go to S0, and then 1 goes to 0. What is our output? Well, the output's 0. Oh, in that initial state, what is our output?
I didn't really get it, I couldn't make sense of it on my diagram.
We don't have an output in the initial state. Outputs are defined by
I'm looking at like everything else.
so we just produce it out. So we have 1,
He said that's a very specific answer.
then we come here, and then our output's now 1.
All these two very
Yes. And then we're here, and then 1 here, and then here, and our output's 0.
Look at my number too, like they didn't.
Then we have a 0, so we go here, and our output's 0.
Yeah. I got like some numbers.
I was like, I don't know.
And then a 1.
I was like, this number's bigger than all the numbers added together.
So raise your hand if you're getting a pretty good idea what this does. So let's think about it like this.
I think it's wait, no,
If you're in state 1, what's the relationship between your input bit and your output bit?
It'll be the same.
They're going to be the same. If you input a 0, you output a 0, and the same with a 1. If you're in state 0, what's the relationship?
It'll be the opposite.
It'll be the opposite. So depending on what state you're in, you either replicate your input or you complement it. And so as you process bits, what states do you end up in on each bit? You start in state 1, that's got the star next to it, that's the initial state. After you read one bit, what state are you going to be in? Regardless of what bit you read? Right? Whatever bit you read, your next state's going to be 0. What's your next state going to be after that? It's going to be 1 no matter what your bit is. So there's 3 things that describe this machine. 1, you alternate states every bit. You bounce between S1, S0, S1, S0, and so on. 2, if you're in S1, you don't change your input. You just copy it to the output. But if you're in S0, you toggle your input to generate your output. So if you put those together and you run it on some sample strings, what you'll see is that basically every other bit gets toggled. Whereas every other bit, starting with the first one, does not get changed. So it complements the 2nd, 4th, 6th, 8th, 10th bits. Does that make sense? So let me draw.
That's so easy. How did I do that?
It's easy once you see it, right?
Yeah. Yeah, once you explain it, it's like, oh yeah, that makes total sense.
what did I do wrong?
I'm another one that can. I think I might want to choose that T, so put it in something.
Should this be 0? Yeah, that's what I'm saying. Oh wait. 1. That doesn't seem like it flipped. What did this do though? This doesn't seem like it complemented it. Well, no, it complemented every other. Oh, it complements every other bit. Yeah.
Here's a 4-state machine.
0, 0, 0, 1.
And try it on that 8-bit input and see what output you generate. And we start in state S00.
So state 1 and it's a 1, so the output will be 0 or 2.
Yeah.
And then S
So
1.
0, 0 goes to
We
itself.
got it.
and the input is
0.
1, 0.
So it'll stay. Yep. It'll go to 0.
And then 0, 0 goes to 0, 1. And
And then
then
state 1, 0, and we have a 1.
And then 0, 1 goes to 1, 0. It goes to 1, 0 to 0.
Yeah.
Do one more transition. Do one more state in there.
Ow, I did 8 and 8. Oh, extra.
Yeah, do 2 more. Do 10 output bits.
How, there's only 8 input.
Oh, okay. Just assume there's zeros or something. No, that's fine like that. You can see the pattern. Tell you what, I'll throw zeros on the end.
Okay. could change it.
That's not what you wrote a moment ago.
State 0, 0.
So I'm pretty sure it was in 0, 0.
I think so.
Let me do it again.
All right, you had it right before. I confused it.
Well, state 0 starting with you going 0, 0.
Yeah.
Input is 0.
So,
Output is 0.
that's what got us there. That's just what it is.
It shifts it over.
Sorry, again?
So, it shifts it over to, you got that's the input, but then what's the output? The output, that's the vertical one. Here, which is, yeah.
I'll message you on Discord for the
So if you're in state 0, 1 and you have a 1, you go to 1, 1. That's 0 on the right. If there's a 0, you go to 1, 0. That's 0 on the left. The arrow in the middle is going back up.
So it's the back.
Okay. Which class?
Here.
Okay.
0.
Yeah, if you can come to the beginning of the presentation, that would be good.
Okay, so we start at 0.
Pretty sure this is right.
Okay.
Here.
Yeah.
0.
Do you not follow this input?
State 0.
Okay.
Might help just find out what state you're in, along with the...
Yeah.
Depending on next input, state 0, 0, 1, 0, 0, 0, 0, and it stays as 1, 1 if it's always 1.
0, 1, input 0, 0.
It's like the same machine. Or
What?
This is like the same.
Oh, not exactly, no.
It helps to keep track of what state you're in.
Yeah, and then, yeah,
Because whenever you get lots of state right here, 0, 0, 0. So it gets you to go to 0, 0, 0, 0.
Oh. Yeah, the input is adding 0 to the
0, 1, 0, 1.
Unless you're doing that.
Just start this whole thing, add 2 zeros to the prime.
Okay.
It's adding
But then try.
So hard to get this.
Okay.
I think this is right.
Yeah.
0 always goes to
Back to state 0, 0.
So it's just adding
If this was a 1, this would still be 0, 0. So we just cut off 0.
Yeah.
So
this is just repeating zeros, or is it repeating this?
Because state 0, 0. 0 just sends it back to state 0, 0.
Now we can do a little bit of adding 2 zeros.
I don't know what has to be.
One of my favorite here.
Does that make sense? So it's 2 bit delay.
Yeah.
You get this?
Perfect.
I'm gonna get my back.
All right, you got it.
Start here. This is given, right? Yes, that's what's given. So remember the first is the one given, this is your output. So start here, you're given a 1.
That means it's going to be.
Yeah, and now you're given a 0. So now you're here. You're in this state now, you're not going to be here. And now you're given 1. So now you're here. So these two options are out.
reality isn't my spirit.
So you have one.
Here I have a 0, so that is
You're on this here. You're on that.
0 forever.
So essentially what it's doing is taking this one here, adding 2 zeros to the front of this.
All right, so what is this machine doing? You feed in a pattern of ones and zeros, how does the output relate to the input?
They shifted to
It waits until the pattern is a continuous stream of ones before switching to a higher D system.
True, and as you said, it basically shifts it 2 bits,
Right.
right? So this is a 2-bit delay, right? So state machines, you always have this clock. The clock is what triggers a state transition. So you've got an input coming in, your inputs are like A, B, C, D, E, F, G, and the clock ticks. The first 2 ticks, your outputs are zeros. The third tick, your output is A, followed by B, followed by C, D, E, F, G. So it delays the input by 2 clock ticks, and then it generates an output. So it's a delay circuit, right? It's kind of what you did with the 555s and the quad latch 74, whatever that thing was, right? But this is the state machine version of it. And the logic behind this, right, the way I designed this was state J, state IJ, basically J corresponds to what your most recent bit was, and the first index I corresponds to what the bit before that was. And this is simply moving around from state to state. And if you're in state 0, 0, it means that you just saw a 0 and you saw a 0 before that. If you get a 1, we go to state 0, 1, which means we just saw a 1, but the bit before that was a 0, which tells us that the next bit that we output should be a 1. And then depending on whether the current bit is a 1 or a 0, we go to either state 1, 0 or 1, 1. So some of these things are actually easier to design than to analyze, right? If you know how to put these diagrams together, you can sort of very deliberately piece together a set of transitions to achieve some sort of behavior. All right, so stay where you are. And let's apply this to language recognition. So same state machine, same diagrams, and so on and so forth. I'm going to introduce one new twist in here, which is if we have a state with 2 circles around it instead of 1, that's what we call a recognized state. And our goal with these types of machines is to know whether or not our input is recognized. So I'm making a diagram I'll put up there. So here's the state machine. It starts in S0 there on the left. If your input is a 1, we move to state S1. If you're in S1 and your input is a 0 or a 1, we move to S2. And if you're in state S0 and your input is a 0, we also move to S2. And S2 is a recognized state because it's got 2 circles around it. And so if we start in S0 and our input is a 0, we move to a recognized state, which means that this is one pattern that the machine recognizes, just a simple 0. On the other hand, if you're in your initial state and you have a 1 followed by a 0, that'll get you to a recognized state. So 1, 0 is also a recognized input. And if you're in S0 and you have a 1, and that's followed by a 1, that also takes you to S2. So that's another recognized string. So this machine recognizes 3 strings, 0, 0, 1, 0, 1, 0, and 1, 1. So if we had a language where those were the only valid words over the language, bless you, then this would recognize something that was valid in that language. So let me add another transition from S2, which says if you're in S2 and you have a 0 or a 1, we go back to S2. So now we recognize these additional strings, any string that we recognized before followed by a 0 or a 1, or any pattern of zeros or ones. It's basically any string that starts with either a 0 or a 1, 0 or a 1, 1, followed by any pattern of ones or zeros, which is kind of like any string. Okay, so let me give you, see, you get how that works, right? Okay, let me give you another machine and ask you to run some strings through it and see what it does. So this has got only 2 states. S0 is our initial state, S1 is our recognized state. So this is a pretty uncomplicated looking diagram. We start in S0. If we have a 0, we go to S1. If we have a 1, we stay in S0. S1 stays in S1 for a 1 and goes back to S0 for a 0. Initial state S0, recognized state S1. So the question is, what sorts of strings does this machine recognize?
Yeah, it's the, yeah, this is a different, so we're just gonna throw it into that string.
Those are recognized.
Is this valid? Because you go to 1, you do 1, which brings you back to S0, and then you just do any number of 1s. We'll just let you do it for as many 1s as you want. And as long as you give me 0 at the end of all those 1s, it's going to give you like, it's going to give you S1. So it's almost like you can have anything as long as it doesn't give a 0. Yeah.
Or 1, 1.
Anything like this. I think it's just everything.
Yeah, you have 0 and then it goes
Followed by.
It would have to be.
Wait, it wouldn't recognize a 1.
Yeah, except for one.
Followed by 0.
I feel like that's the only thing you can't do. Zero would be recognized, but it wouldn't.
You can have any number of zeros, but they don't be connected. Ones in between.
Like 000 would be recognized, and 0 would be recognized. It would have to be odd number of zeros. Really strange. Yeah, there's some things that doesn't work on.
So it either be
It works on most things.
1 followed by any number of 1 followed by 0 followed by any number of 1 followed by 0 repeating. Or it can start with just a 0 followed by any number of 1. You can never have more than 1 0. As long as you have 0 strings like that, you can do this. So.
Can I suggest some strings to try? So,
0 or 0.
well, it might have been kind of random.
Like that, I think this works.
Oh, yeah, you can have
Any amount of 1s and odd amount of 0s. Go back to an any amount of 1s
Yeah, so-
and odd amount of 0s. Well, I know, what do you mean?
But it would be arbitrary.
So it's 1 followed by 0 followed by 1 followed by 0.
0 and 1.
Yeah, the zero, I mean, kind of one. I think that might.
Yeah, so that's where you get any number of 1s.
Okay.
And so, or you could go like this with 0.
Any number is zero.
It's
So
a
what
lot.
number should two
I know, it does, it's really,
So it's only the recognize one side. So if you're going to have a 0, it has to always be an odd number.
Oh, what it is.
So it's an odd number of 0.
When that's given for the one, so it can just be a random out of zero, it just stays the same. So it's a polynomial. So it's like a button. Yeah, the notation.
Because when they recognize one side, it's ending
Weird. I didn't mean as an exponent, I meant there's.
What it is the one.
And one, zero.
This is the thing where I'm getting tripped up on is like, if you do like 1, 0,
Oh, actually,
1, 1, 0, 1, 0, 0, that's valid.
Yeah, you never are getting.
I sent it backwards.
Does it just need to be with 2 zeros?
So there.
Wait, actually, this isn't valid. This is valid.
And from there, you need an odd number of 0s. Recognize means those are the only ones that so all the ones going to zero,
there's so many.
they aren't recognized. So like if you had a 111 is the only thing. So it's not zero. This is only the bit of where it outputs from. And everything combined and then there. So it has to be an odd number of zeros. Even at any point it can be.
It can start with a one, as long as a zero follows. We start at stage zero.
You have to be saving that.
So that, those outputs just avoid.
Because it can you can have 1 0 and it'll output.
Do either, do both zeros and ones, or force you to change?
Or-
It don't have to be state one.
Yes, that's what the double
Zero,
circle
zero, zero.
And so when you go back to
If you're at stage
you're
zero,
not
what
ready to
inputs?
another
Zero changes state.
Only odd
If you're in state zero and you get a one, change state.
No.
Okay, what about if you're in S1 and you get a one? Okay, if you get zero, you change
You're
state.
here, you start with 1
Or you're the zeros that are changing
If
state.
the 0
So if you
is
start with
odd,
1, you'll
you
do
can
1.
do any amount of 1.
You said you're a 0 or now you're up here, this is an output. Right, or you can do the same thing, and then you go 0,
And then if you have an even amount of 0s,
but you're
you
not.
can do any amount of 1.
0.
This proper
Yeah,
formula?
if you go to the end.
Well, he has 1 0 0 and 1 0.
But if you
Which
have
you
one,
can't, okay, I see.
And then you have the one
And you
right
have
below
ones
that.
and if odd zeros.
Yeah.
And
Yeah.
But you're gonna have odd amount of zeros, and then you have to have an odd amount of zeros, and then how many other zeros, and you can just go back to
Yes.
But suppose
Although I don't know how one.
it doesn't.
Well,
you
you're
just
state one
say
plus.
zero in that case.
And do the state one plus.
When you're looking at this, you start at stage one.
You start at stage zero, so you would just go back to stage zero. But then you never go to S1.
Oh, you're talking about the zero one. Yeah.
How do you get output of one? You start at stage zero, so there's no way to get a one at the output.
There's no outputs being generated here.
Oh, okay.
Those are just.
Oh,
Say
yeah.
0, 0
would work either.
Yeah.
Return back to, so SR last.
Yeah.
0, 1, 0, 1, say it would be 0, 1, 0, 1 would be 0, 1 would work. And 1, 1 for an SR, 0 would work. So.
Seems like the ending of the line needs to be a zero or a zero followed by any number of ones. Yeah, must end with a zero followed by any number of ones.
Okay. I mean, you can build this with one last case logic.
And then every zero before that.
We're trying to figure out.
Who needs a new marker?
It basically doesn't matter.
One new marker. Who else needs a new marker?
0, 1.
Just two people and you're ready.
Will the 0, 0 be an?
We have 9.
Yeah, just in case. Basically rules. Not really like that.
So, let the professional know. So the 0.
That doesn't work for all of them, because if you have a 1,
Brand new marker.
oh wait, no, 1 and 0 followed by any number.
Who else wanted a
Maybe
marker?
that works, it's just anything
S1 output 1, 0.
followed by a
Who
zero.
said they wanted a marker?
That makes sense. It's
So what's
probably
your
a simpler
takeaway on
way
this
to write
machine?
that, with just anything followed by a zero and any number of ones.
It ignores ones effectively, right? If you're in state 0 and you got a 1, you stay in state 0. If you're in state 1 and you got a 1, you stay in state 1. So the ones don't affect what state you're in. Which means if you're in a recognized state and you get a bunch of 1s, you're still going to be recognizing the string. And if you're not in a recognized state and you get a bunch of 1s, you're not going to recognize that string after a bunch of 1s. So the 1s don't change whether or not it recognizes an input. So when we're studying this, we can throw away the 1s and just look at what zeros do to it. So it starts off in state S0, that's not a recognized state. If you get a 0, what happens? You change state and it's recognized, so it recognizes 1, 0. If you get a second 0, what happens? It goes back to 0, it's not recognized. If you get a third 0, right, it's exactly like when you got the first, it goes back to being recognized. So if you get an odd number of zeros, you're in a recognized state, and the 1s don't affect whether you're recognized or not. This whole machine simply detects strings with an odd number of zeros, which is kind of cool.
Well, it wasn't even until like the last article we were working on, I was like, everybody explained that, I was like, oh, you could do 1, 0. I was not even paying attention.
Okay, so here's a question to think about. We know that we can detect an odd number of zeros. We could make a machine that detects an odd number of 1s. Can you make a machine that detects whether you have the same number of zeros and 1s? So think about this, talk about it, try it for about 5 minutes.
The only thing that would be the first.
Within a 1, then we want to live to a unrecognized state. But if we put a 0,
Technically, we have the same number of
the
zeros.
1 here, but if we had a 1,
Stay here to begin at least.
You need infinite states, I think.
yeah, I think you're right.
So you need one to.
Unless there's a clever way you can go without infinite states.
Didn't even take you a minute to get to that conclusion.
So does the value?
Yeah, so if it's a finite state machine, you cannot, because you need infinite states.
That way, start out, wherever you have all you can add there, then you always should be using the same amount of.
But if you could make an infinite state machine, you could do some things.
Yeah, I bet you could.
So, if we have a 0,
Not
1,
me,
here,
someone
we'll call that
can.
x is 0. And then we'll call this one x is 3. And then
I mean, I might be wrong, but it's
a 1 sends into here,
Except that doesn't,
because then we'll call that
if
1 would
But
send
you
to
could
x.
make a finite one in case specified counts for matching, like
so.
10 bits that have matching amounts. It'd just be a really big state machine.
yeah, but then you're right.
I don't know. I mean, in the previous hours.
When you run into the same problem.
Here you have now an
No,
extra.
like, if you have 10 digits,
Oh yeah, you landed them on.
And now what?
yeah, that's what I was
Oh,
saying.
yeah.
If you make it finite, you could represent it
Yeah.
finitely.
Yeah, definitely.
So you do it,
But yeah, you don't know how many digits you have. and it's impossible.
unless this is.
So 1.
Does it have to be a finite state?
Yes.
Oh.
Recognize state, we're going back to
So if you have start here,
Yeah.
and you have a 1, then you have a 0, now you recognize that, and you have a 0, 1, you recognize that. Or you get to here, so you go 1, 1. Now how do you keep track of your next, another extra 1?
Right here, you have either a 0,
State.
one.
Okay, I see what you're doing.
Two.
That makes sense.
Here, yeah, you want it to be.
So what's the record? So this is impossible to have an infinite number of states, or also
Correlation between like
we're got the access and what to do once you already have the access.
Yeah.
Is there some correlation between numbers that have finite zeros and negatives?
And then we can guarantee where.
Probably not.
But
I mean, like, if you have something that, like, runs on one,
Yeah.
and then, like,
We're doing 2 bits.
like, if it's special
So here
hand,
you need.
to, like, do something on one, and do something else on zero,
But.
then you could ensure that something that's always done is always able to do.
Here, but
Yeah.
then you, if you had like a 0. Right, but it would still be like 0.
There's two ones, two more ones. So it's the same, and then you go back. So kind of
There's no lamp today.
Yeah, we keep branching off until.
The one due tomorrow.
Or if you have something included in your state that recognizes.
due tomorrow?
past
The informal? I thought I was doing Thursday.
No, the CSC 215.
Oh,
We got 224.
okay.
And what about Morse?
Oh, the Morse code one? Oh, that's due tomorrow. I've already gotten it graded. I thought I was here a while ago.
No, these are mine.
He's already graded mine.
All right, so let's go ahead and sit down, let's talk about this.
Is that your passage?
So, So somebody just made the comment, I can't think in state machines. Most of us cannot think in terms of state machines, right? This is not a natural way to go about solving problems, right? You can get good at it, which is a little worrisome sometimes. If you spend enough time playing with these things and analyzing them and putting together circuits, you actually can start to think in these terms. But it's not a very natural mindset, right? So let me ask you this. Could you write a C program that takes in two strings of ones and zeros and tells you whether or not they have exactly the same number of ones and zeros? Sorry, one string of ones and zeros tells you whether or not they have the same number of ones and zeros.
Yes.
You think so? It depends on how much of a troublemaker your teacher is when they test your program. So we run this on the Linux server. Let's say it has 4 gigabytes of main memory. That's 32 gigabits. What's the largest integer I can store in 32 billion bits? Right, 2 to the 32 billion, maybe minus 1. So what if I put in a string with 2 to the 33 billion ones, followed by 2 to the 33 billion zeros? Is your program going to successfully be able to tell me if I put in the same number of ones and zeros?
Will you even be able to successfully put in that number?
I got a lot of patience. I'll just keep typing and counting.
The computer will stop being able to store it, though, won't it?
Well, you'll have to read it in pieces, like one keystroke at a time. But your computer cannot count up indefinitely high, right? Even if you use something that like does arithmetic in memory, goes beyond the regular 32-bit integer or 64-bit integer limit, there's a limit to how high a computer can count. And the limiting factor is the amount of memory you have, because counting takes memory. You've got to remember what number you're at in order to add 1 and go on to the next number. And if you've only got 32 billion bytes of memory, 32 billion bits of memory, there's a limit to how high you can count.
All right, then just download more RAM.
And you just download more RAM.
Okay.
just do a RAM fork. Make twice as much RAM.
Therefore, then you have other memory.
So finite memory is a constraint, right? And when we talk about finite state machines, the number of states corresponds to basically how much you can remember. The main game you're playing when you design a finite state machine is you're using states to remember information about your system. So when we build a traffic light system and we have a state over here and a state over here, what we're doing is we're trying to remember some piece of information. The fact that 20 seconds have passed since this light turned green, right? We store that piece of information by going into a new state. When we're in this state, we're storing the piece of information that this light is turning yellow, right? So your states basically correspond to your memory. And so on a finite state machine, this is actually impossible because you need to have an infinite number of states to be able to store an unlimited number of ones or zeros. Now, you're not going to input an infinite number of ones or zeros, but there's no upper bound on how many you might put in. You might put in a gazillion to the gazillion ones before you start putting in any zeros. And you got to be able to remember that piece of information so that you can subtract off as you get zeros in and see if you have the same number. And these states basically correspond to the memory we have in our modern computers. Because again, our computers are functionally equivalent to state machines. And they're equivalent to a particular type of state machine called a Turing machine. So Turing machines were developed by Alan Turing. I don't think he called them Turing machines. But he developed them as a way to model computation. And it wasn't so much for the sake of building a computer so that we could have laptops and make web browsers a few hundred years down the road. Turing machines were developed as a way to study algorithms. And there were fundamental questions that mathematicians and logicians and philosophers were studying in the 20s and 30s about what is and is not computable. What can we do with an algorithm, or what can't we do? And in order to answer that question, you need some way to formalize what do we mean by an algorithm? What do we mean by doing computation? Because you and I have a kind of hand-wavy notion of what computation is, right? Well, you take some stuff and you do things to it, right? But to be able to do mathematical proofs and show what you can and cannot compute, or how long it takes to compute things, stuff like that, you need to have a formal model of what it means to execute an algorithm. And so a Turing machine was imagined as a theoretical computing engine before we really had general purpose computers, and then at some point this actually turned into some of the early machines. So let me give you an intro here. So let's define a Turing machine T. And it's an ordered set of four things: S, I, F, and S0. So S equals a set of states, just like a state machine. I equals the alphabet, which is a set of symbols. And a lot of times our alphabet will just be 0, 1, and maybe a few placeholders. So it's kind of like the symbols from Automata. S0 is our initial state. That's the state the system starts in. And F, we're going to do this in a fancy way, but I'll explain it in plain text. It goes from the Cartesian product of S with I. It's a mapping from the Cartesian product of S with I into the Cartesian product of S with I with this set containing two elements that we call R and L. And so this S is our current state. And this I is an input. So it's some symbol from our alphabet. And F takes us from a current state and an input into a next state, an output, and a direction. So that's the fancy sounding mathematical description of a state machine, but let me draw you a picture of it instead. So picture a piece of magnetic tape, or maybe paper, and it's infinitely long, okay, but it's coiled up on these two spools, and this tape can move left or right, and there's a read-write head sitting above this. So this can do two things. One, it can read some symbol that's printed at this position on the tape, and it can modify that symbol. So if it's magnetic tape, it can just electrically read what it is and write it, or it might be, you know, a print head with some whiteout in it, so it can erase this symbol and put something new in its place. And we make a state transition table that looks like this. We have a present state. We have some symbol, which is under the read-write head. We have a new state. We have a symbol that we're going to write in that position. And then we have a direction that we're going to move the tape, either one spot left or one spot right. And this is what the state table is going to look like for a Turing machine. So it's an infinitely long tape. We have a set of states. And at any point in time, whatever state we're in, we find a transition that matches the current state and whatever symbol is under here. And when we find a state transition that matches that, we write this symbol onto the tape, we move into a new state, and we move the tape either left or right one spot. And it makes more sense physically to move the tape, but I'm usually going to talk about moving the read-write head because it's just easier to draw. Because we'll use an arrow to say where the read-write head is moving, and we'll just move that back and forth, left or right. Okay, so Wednesday we're going to start with this idea. Okay, so of this general Turing machine, we'll start looking at some programs and analyze them by following this. We'll see what those state programs do, and then we'll start doing some synthesis. And this is much more fun than state diagrams usually, to try to design machines that do certain behaviors like recognize things or add and so on. We'll look at some simulations. We'll talk about what this can and cannot do, and we'll probably wrap up Wednesday by talking about something called the halting problem. And it's a fundamental problem in computer science, and it ties into state machines. And then Friday we'll do review. I'll post a review for 2:15 probably later today, probably tonight, on Canvas, and we can talk about that ahead of time. But we'll do a review on Friday. All right, so I'll see you next time.